What? There's a reason behind why things work? You mean they don't just get plopped into a textbook? Of course. You know I'm all about the why. So why do Taylor polynomials work? Why? So we know that the key idea here is that all derivatives of all orders at the place where you're approximating some function f needs to be equal to all derivatives of the polynomial that is approximating that function f. So in other words, as long as when I plug in c into my polynomial, I get out f of c, then we start out exactly where the approximation point is on the curve. Like imagine if I have like a tangent line to this point right here. And I wanted the approximation to start here. If I had f of c not equal to that point, I'm already off of where I'm approximating. So we need to start out where the y value is of our approximation. So to show this, I'm going to show you why the Taylor polynomial ends up giving you all these values to be true. That all orders of the derivative at the place where we're approximating is equal, whether we plug it into the function or into the polynomial. So we're going to show that f of c is p of c. To do that, just plug in c into all these. Now what happens? Well, you get f of c plus, and I'm just going to do this in the very first term and then expand it out, f prime of c times plug in c for x. That's p of c that we're doing. Oh, if I plug in c here, that goes to 0. So does this. C minus c, that's 0. C minus c. They all go to 0 except for the first term. So that ends up equaling to f of c. So that means p of c is equal to f of c. Good. Now we got to show that the derivative at that place is equal. Let's check this out. So I'm going to take the first derivative. So p prime of x is equal to, watch what happens. This goes away because that's a constant. And then this right here, we just get the constant left over because all that goes to 1, right? Derivative of c is 0, derivative of that is 1. So that's equal to f prime of c over 1 factorial. Plus, check out what happens here. We get 2 times f double prime of c all over 2 factorial times x minus c, right? That's just the power rule, this coming out front. Those completely cancel out. All right, more on that in a little bit, but when I plug in, and then it just keeps going on, I'm not going to keep taking all the derivatives, then p prime of c is equal to, wait a second, well that's f prime of c. When I plug c into this, we get 0, and every other term still has an x minus c term, because this 3 would have come out front with the derivative, leaving you with a 2, but it's still c minus c. So everything else zeroes out. So p prime of c equals f prime of c. Check. All right, let's go out to the second derivative. So now we've taken the first derivative. The second derivative, now that we've done that, is equal to, well, the first derivative is now a constant. That goes to 0. This f double prime of c becomes just f double prime of c. Oh, the 2's canceled. And that went to 1. Now this one up here, and I'll just kind of write this in the first derivative part, went to 3 times f triple prime of c all over 3 factorial times x minus c squared. That was the first derivative of that term. If we do the second derivative of that, I'm going to keep it unsimplified. I get 3 times 2 times f triple prime of c times x minus c. That 2 came out front here, all over 3 factorial, plus, and so on and so forth. Now wait a second, look what happened. This will go to 0. And every other term after the third power has x minus c in it. So all those terms go to 0. So therefore you get p double prime of c equals f double prime of c plus 0. So they're equal to each other. So we're showing that the derivatives of the function and that we're approximating and the approximation polynomial are equal to each other at every order of derivative. Why is this? We're just now going to take a look at the nth term. So if I take any number of derivatives up here, look what's happening here. Just with the third term. The first derivative, you would have the 3 come out front. The second derivative, the 2 came out front from here. And the first derivative, the 1's going to come out front. So if you think about it, if you have any polynomial, let's not call that f, let's just call that g of x. And you take any number of derivatives, g prime of x would be nx to the n minus 1. G double prime of x would be n times n minus 1 times x to the n minus 2. G triple prime of x would be n times n minus 1 times, do you notice what's happening here? Dudes, you are getting n factorial right there. So g to the nth derivative of x is equal to n factorial times x to the, and then whatever power you have up there. Eventually it's just n factorial and then x to the 0. So you just end up with n factorial as it goes away. So the whole point is that this, all of that is going to n factorial, and this is just the previous term minus 1. Oh my word. So if we take a look at the nth derivative here, well, think about this then. All of these n powers are going to come out. N times n minus 1 times n minus 2 times n minus 3, and eventually the nth derivative of p, I'll write that as the nth derivative of p of x, is going to be equal to n factorial times f to the nth derivative at c. That goes to 1, and that's over n factorial. They divide out, and you end up with this. So the reason why we need the n factorial down here is because every time you take a derivative, eventually this thing's going to head out to n factorial. This went to 3 factorial. 3 times 2 times 1. 2 times 1, just 1. That's what happens with powers that go up by 1, which is what the Taylor polynomial does, and that's what allows us to stay true to that idea that we need the derivatives at all orders of a Taylor polynomial to be equal to the function's derivatives of all orders. Oh, it's beautiful. I'll see you in the next video. Peace.